Hello AP students. Today we are discussing random variables. This will be our last lesson where we focus on these. We're discussing random variables in the normal distribution. So basically, if a random variable is described as being approximately normally distributed, that means we can use the standard normal distribution and z-scores to answer random variable questions. Okay. And these would be continuous random variables. Okay. So example 1 says, suppose a large bowl of cereal holds an average of 4 ounces of cereal with a standard deviation of 0.5 ounces. So we have the mean bowl of cereal is 4 ounces, and the standard deviation of the bowl was a ½ ounce. It says, suppose a large box of cereal contains 16 ounces of cereal with a standard deviation of 0.1 ounce. So this is the mean. I'm going to spell out box is 16 ounces, and the standard deviation of the box is 0.1 ounce. Okay. So it says, if we pour a bowl of cereal from the box, what is the probability that the box contains more than 13 ounces of cereal? So after I pour the bowl, what's the chance that the box has more than 13 ounces in it? Okay. And it says, assume both variables can be modeled by a normal distribution. So I'm taking my box of cereal, which has 16 ounces, and I'm pouring out a bowl, okay? Which means you would expect about 12 ounces of cereal left in the box. However, obviously we don't know for sure how much was in the box to start with, because there was a standard deviation of 0.1 ounce. And for the bowl, we know that it can hold, the standard deviation is about a ½ an ounce. So I can find the combined, the mean of what I think is left in the box is 12 ounces, but I should figure out what the standard deviation is of what's left in the box. So for that, remember, I can't just add or subtract the standard deviations. I have to add or subtract the variances. And remember, we never subtract variances, we can only add them. So I'm going to take 0.5 is the standard deviation of what was in the bowl. I'm going to square that, and I'm going to add that to the standard deviation of what was in the box, which is 0.1. I'm going to square that, and then I'm going to take the square root of both to find out the combined standard deviation. So 0.5 squared plus 0.2 squared is 0.26. And then I will take the square root of that, which will give me my combined standard deviation, which is 0.51. Okay. So when I subtract the 4 ounces for what I poured into the bowl, I end up with a distribution that has a mean of 12 ounces and a standard deviation of 0.51 ounces. Now, since both variables, the bowl and the box, were normally distributed, the difference between them should also be normally distributed. So now the question is, if we pour a bowl of cereal from the box, what's the probability the box contains more than 13 ounces? So here's 13 ounces. I'm going to shade to the right. And then since this is a bell-shaped curve, a normal distribution, I can use a z-score. So I'm going to use a z-score and do 13 minus 12 over 0.51, which gives me a z-score of 1.96. And then to look that up, I would do normal CDF, 1.96 to 10, because I'm going to go off the graph to the right. And on my calculator, I get about a 2% chance. Okay, so not a very big chance that I'm going to have over 13 ounces left in the box. And that's basically because the standard deviations are very small. So there's not going to be much error here. One of the things to understand, though, and keep in mind, even though we subtracted the means to find what was in the box, we still add the variances, okay? That was a big part of this unit. So hopefully everybody's understanding that. Let's do another example. Example 2 says the annual medical cost for dogs is $100 with a standard deviation of 30. So I have the mean dog is 100, standard deviation of the dogs is 30, and it says the annual cost for our cats is 120, So cats seem to be a little more expensive, and a standard deviation of 35. And they're a little more variable, the cats are. So it says, assume the annual medical costs for dogs and cats are normally distributed. How much more expensive will it be to own a cat than to own a dog? Well, it's going to be the mean of the cats minus the mean of the dog. So 120 minus 100, which is $20. So on average, the cat's going to cost $20 more than a dog. It says, what is the standard deviation of the difference in cost? Well, remember, for this, we're going to add the variances of the cats and the dogs to find the combined variance. So I'm going to do 30 squared plus 35 squared. That looks like a period. I didn't mean to. And then remember at the end, I'm going to take the square root to find the combined standard deviation. And this is another example where I subtracted the means, but I'm going to add the variances because remember that's what we did. So doing this calculation, I get 2125 as the combined variance. And then I'm going to take the square root of that, which gets me the combined standard deviation, which is 46.1. Now, my next question. What % of the time will it be more expensive to own a dog than a cat? Well, these are kind of interesting. When I want to know when it'll be more expensive to own a dog than a cat, I'm going to make a distribution of their difference in cost. And the difference in cost is $20 with a standard deviation of 46.1. That means that 20 stands for the cat costs $20 more. So if you think about this, if I marked a spot on here at 15, that's where the cat costs $15 more. Over here, that's where the cat costs $10 more. I want to know, when does the dog cost more? Well, at 0, that is when the dog and cat would be exactly the same price. Okay, when their difference in price would be 0. So the place where the dog starts to be more expensive is when the difference ends up to be negative. So I want that red shaded area. So this is kind of a common question in this unit. When I want to know when does the distribution flip from one thing being in the lead to the other one being in the lead, we're always looking at the spot where the difference is 0, because at that location they are tied. And then I just want to go to the opposite side. So I'm going to do a z-score for 0. Okay, so it'll be z equals 0 minus 20 over 46.1. And it gets me a z-score of negative 0.43. And then I'm going to look this up using normal CDF. And this time it's going to be negative 10 to negative 0.43 because I want the left side of the graph. And this time we get a 33% chance. So even though the average difference in price is that the cat costs $20 more per year, there's still a 33% chance that the dog is going to be more expensive. And part of that is because of the very large standard deviation, which means there's a really high variance in events that could happen here. There's a $46 swing in either direction from that $20 average difference. Okay, so that's a pretty common type of question that you're going to have to deal with in this little mini unit. All right, we're going to do one more example. In this one, it says, example 3, the heights of high school boys and girls are normally distributed, with the mean boy is 68 inches and the standard deviation of 3 inches, and the mean girl is 64 inches with a standard deviation of 4 inches. Now it says, suppose there's a 5-on-5 rec basketball league at school. This is like intramural. There must be 3 girls and 2 boys on the team. A team is disqualified if their mean height exceeds 69 inches. So what is the probability that a team that is randomly assigned will exceed the maximum height requirements? So first of all, let's figure out what is the maximum height requirement. Okay. Well, if the mean is 69 and you can't exceed that for your 5 players, then the total height that we need to stay under for our team is 345 inches tall. Okay. Now, every kid's not going to be 69 inches tall, but the average can't be more than that. Okay. So that's my limit. Now let's make our team randomly. So 3 girls, each averaging 64 inches tall, would be, 64 plus 64 plus 64. And then I have 2 boys, and they would average 68 and 68. So usually this will be the average height of a randomly selected team, which would be 328 inches. So the average team is going to be under the max, right? Underneath the 345. But, every kid's not going to be exactly those heights. We have standard deviations involved here. So first, let's look at the standard deviations of the girls' heights, which would be 4, 4, and 4. And the standard deviations of the boys' heights would be 3 and 3. But remember, I can't add standard deviations. I have to add variances. So it's going to be 16 plus 16 plus 16 plus 9 plus 9. Which is 66. That's the combined variance. So I need to take the square root of that to get the combined standard deviation. And I get 8.1 inches. So normally the teams are going to look like this. The average height would be 320, or the average total height would be 328 inches with standard deviation of 8.1 inches. And the maximum a team can be is 345. So that's over here to the right. And any team taller than that is disqualified. So I need to know, what percentage of the time is that going to happen. That was the question. What probability that the team is randomly assigned will exceed the maximum height requirements. So I need to do a z-score again. So this will be z-score equals 345 minus 328 over 8.1. Which is about 2.10. I had to round that. So now I need to look up that red area, which we get by normal CDF, 2.10, comma 10, because I want to the right. And I get about 2%, about a 2% chance. So a very small chance that if they randomly put these teams together, that you're going to get a team that's too tall. And obviously they're trying to keep the teams fair, so they've set that max height requirement. It's only about a 2% chance. Okay. Again, one of the key things here is you can add means, right? And that's fine. But you can't add standard deviations. You have to add variances. Okay. Which is why we have this row right here. We turn those standard deviations into variances, added them up, and then we take the square root to get them back to the standard deviation units. And remember, we never subtract variances, right? That was a key point of this entire unit. So good luck with randomly distributed, or random variables that are normally distributed.